Hi, this is Alex from devstories.eu. LangChain v1.0 Orchestration Framework, Episode 19 of 20. What happens when an agent built in Python needs to natively converse with an agent built by a completely different team running on a completely different server? If you rely on hard-coded internal function calls, your system breaks the moment it crosses a network boundary. The solution is agent-to-agent communication. Agent-to-agent, or A2A, is a communication protocol that enables truly distributed multi-agent systems. It allows agents hosted on entirely different servers to maintain a continuous conversation without needing to share the same underlying codebase or local memory space. Instead of wrapping everything in a single massive application, you route requests over the network. The communication strictly relies on a defined endpoint format, /A2A/ followed by the assistant ID. Every agent participating in this distributed network exposes this exact endpoint path. When one agent needs help from another, it sends an HTTP post request there. The payload sent to this endpoint is structured as a standard JSON RPC message. To keep the conversation coherent across multiple network hops and different servers, the protocol uses two distinct identifiers in its payload. Developers sometimes confuse these two, so we will define their boundaries. The first is the context ID. The context ID is responsible for overall thread continuity. It represents the entire overarching conversation history from the first prompt to the final output. The second is the task ID. The task ID identifies the specific request or step within that single turn. Context ID spans the whole session. Task ID changes every time one agent asks the other to perform a new action. Consider a practical scenario where Agent A is running on a server listening at port 2024, and Agent B is running on a different server at port 2025. Agent A realizes it needs Agent B to handle a specific subtask, perhaps checking external inventory. Agent A prepares a JSON RPC message. Inside this message, it includes the existing context ID, so Agent B knows which ongoing conversation this belongs to. Agent A also generates a brand new task ID for this specific inventory request. Agent A sends this payload to the A2A endpoint on port 2025, inserting Agent B's specific assistant ID right into the URL path. Agent B receives the request. It reads the context ID to recall any necessary background state, processes the task requested in the JSON RPC parameters, and computes the result. Agent B then constructs a JSON RPC response. This response explicitly includes the exact task ID that Agent A originally provided. Agent B sends this response back to Agent A on port 2024. Agent A receives the result, matches the task ID to its pending request, and continues its own internal execution. Here is the key insight. Because the protocol enforces standard JSON RPC and isolates state tracking into specific context and task identifiers, neither agent needs to know how the other operates internally. They do not maintain a constant open socket connection. They simply take turns passing structured messages back and forth across standard HTTP boundaries. One server asks a question, the other answers, and the overarching task progresses. When you separate the long-term conversation thread from the individual short-term task execution, you can scale multi-agent networks across different servers and frameworks indefinitely. If you find these episodes helpful and want to help support the show, you can search for Dev Stories EU on Patreon. That's all for this one. Thanks for listening, and keep building.